Today we start talking about Chapter 12, which brings a lot of the ideas that we've developed during the semester together. The topic we're going to be talking about is called statistical mechanics, and the basic idea is that you apply ideas from probability and statistics to understanding the behavior of objects in the world. And we're going to be the goal is to understand in detail and to develop a microscopic explanation for some of the things that we've talked about during the semester. For example, a clear idea of what temperature is. We know that it's roughly related to average energy, but how? We're going to talk about entropy, and we're going to actually find that we can predict from a microscopic model and simple principles the specific heat capacity of different solid materials, just from what we know. It's sort of, I like this topic. First of all, it brings a lot of ideas together, and second, it actually really isn't very hard. It's kind of a nice way to end the semester. There's nothing that sort of bends your head very hard, although you do need to learn some new things, but none of it's terribly difficult. So the basic idea is actually one contained in this question, which is, suppose you have a cup of hot coffee and you put an ice cube in it. You'd probably be surprised if the ice cube got colder and the coffee got hotter. However, would that actually violate the energy principle? So most people say no, it actually wouldn't violate the energy principle. And that's correct, it wouldn't. We have the change of energy of a system is work done by the surroundings plus energy transferred into the system due to a temperature difference with the surroundings. But the styrofoam cup is a pretty good insulator, so it insulates the coffee from the surroundings. So if you say the system is the ice cube plus the coffee, we say there's no energy input from the surroundings, and so that must mean that the change in energy of the coffee plus the change in energy of the ice cube equals 0. And that could be true if the ice cube got colder and the coffee got hotter. So the energy principle just says energy doesn't disappear. It doesn't say which way it's going to go. So the energy principle doesn't give us any constraints on which direction energy is going to flow, even though we all know that it's not particularly likely that the ice cube is going to get colder and the coffee is going to get hotter. The same reason, here's a table. It has some thermal energy. The atoms in the table are jiggling around. I put this marker on the table. Now suppose that we saw the marker suddenly jump far up into the air and the table got a little colder. The thermal energy in the table went down. Would that violate the energy principle? No, it actually wouldn't, would it? That the energy could flow from the moving atoms in the table into the pen, and all the atoms in the table could end up moving up together in such a way that the pen would jump a couple meters in the air, but we'd probably have to wait a long time before we saw that happen. So it's not that it's impossible. It's just that it's very improbable. And in order to address the issue of what things are probable and what things are not probable, we actually have to talk a little bit about probability. And the probability we're interested in occurs on the microscopic level. We're going to look at energy going into systems at the microscopic level. And basically the question we're going to be asking is, what's the most probable distribution of energy within one system, or two objects in a system, or whatever. So what we're going to do, we're not going to introduce any new ideas. We're just going to go back to something we've talked about all semester, which is the ball and spring model of a solid. So we're going to talk about solids, solid metals, just because they're simpler, but the basic ideas apply to other things. So remember that we have this model of a solid as a bunch of massive atoms connected to each other by chemical bonds, which are spring-like, and they're all vibrating. And remember that for a mass on a spring, quantum mechanically, we found that we can draw a potential energy curve for a mass spring system that actually, for the ideal mass spring system, it's a parabola, and that the amount of energy you could put into vibrations for one of these small systems had only certain possible values. So in the ground state, there was some amount of ground state energy that you can't get rid of. And to get to the first excited state, you put in what we call one quantum of energy, 1 times h bar omega 0. And that puts more energy into the system, so the sum of k plus u is that much larger. We could excite it to the second excited state, and all the states in the system are equally spaced. Each time you just add 1 quantum of energy to go to the next state, you're adding the same amount. So that's a one-dimensional, we call it a quantum oscillator, and you put in, so 1 quantum of energy just refers to the amount of energy you need to go from one energy state to the next. However, the real world is in fact three-dimensional. So what do we think about in 3 dimensions? Well, it's not really very different, except that suppose we consider one atom in our solid. It can oscillate in the x direction, the y direction, or the z direction. And presumably we could put energy, 1 quantum of energy, into the oscillations in the x direction, or 2 quanta of energy, or 3 quanta of energy, or 4 quanta of energy into oscillations in the x direction. Or instead we could put it into the y direction. Or instead we could put it into the z direction. Or we could spread it around, so we put 1 here and 1 here and 1 here. So there are various ways to put in however much energy we have. Now, mathematically, the basic simplification we're going to make to this model is actually represented by this box. So when you have lots of masses connected by springs, one mass moves, that affects the next one. That's how we talked about speed of sound in a solid, disturbance propagating down. We're going to simplify this model for the purposes of talking about probability and energy by saying that we're going to consider every atom to be independent of its neighbors. So each atom is oscillating independently, and it's as if when we have this ball, so here's remember we called it a lattice of all these balls, which are atoms connected by chemical bonds, all linked. It's as if we said, well, instead of being connected to neighbors, we're going to model them as if we had put rigid walls around each atom, so each bond was connected only to a rigid wall, and that meant that motion of this atom didn't affect that atom. Now there's some problems in terms of causality. This model doesn't tell you how long it's going to take for energy to travel from one end to the other. But it does allow you to do a mathematical simplification that allows you to think about where the energy is. So we're going to not specify the mechanism by which energy might get transferred from one atom to another. We're just going to think about different states and how. Now this model is actually due to Albert Einstein. So this is called the Einstein model of the solid. It says that instead of all these coupled balls and springs, we're going to consider atoms to be masses connected to springs that aren't coupled. And in fact, we're going to simplify it even a little more by saying that oscillations in the x direction and the y direction and the z direction are actually independent. And so instead of considering this somewhat more complex situation, we'll say that we're going to abstract our model and say that this atom, which can move in the x, y, and z directions, is really mathematically the same as having three masses on springs. So you have one that can oscillate only in the y direction, and you have one that can oscillate only in the x direction, and you've got one that can oscillate only in the z direction, and they're completely independent. So we're going to say every time we think about one atom, we're going to mathematically model it as if it was three separate balls and springs, one in x, one in y, and one in z. So we call this the Einstein model of a solid, the Einstein solid. And one atom is modeled as three independent oscillators. And we'll keep coming back to this because this is the key idea. This is the idea that's going to get us through this discussion. And it's an abstraction, right? I mean, it's a simplification of the model. It's an abstraction, but it works. So it eliminates some complexities. It's just a lot easier to work with than a model where we had to consider the interaction of every atom with its neighbors. But if we're just considering distributions of energy, it should actually be something we can work with. And the reason it works mathematically is that for a three-dimensional, for one of these oscillators oscillating in three dimensions, we can write down the equation for the vibrational kinetic energy and the spring energy. So K plus U. So one atom in 3D, we have K vibrational plus U spring is equal to, well, this is just kinetic energy. It's half mv squared, or remember that's equivalent to p squared over 2m. So we can write this as the momentum squared over twice the mass of the atom. And the spring potential energy, half K sub s, s squared. However, in three dimensions, of course, the momentum is px, py, pz, and so the magnitude of p squared is just px squared plus py squared plus pz squared. So we can actually write this, and if we consider the stretch to be a vector, we could talk about stretch is a vector from the equilibrium position to the current position. then S squared is just the x component of the stretch squared plus the y component of the stretch squared plus the z component of the stretch squared. So what we've got is px squared plus py squared plus pz squared over 2m, where that's the mass of an atom, plus a half, so I'll write ma, k sub s interatomic times sx squared plus sy squared plus sz squared. And then just rearranging the terms, we can end up writing that as grouping the x components together and the y components together, and the z components together. And so this is just like one oscillator oscillating in the x direction. This is one oscillator in the y direction, and that's one oscillator in the z direction. So mathematically, it actually just works out that this looks it separates and looks like their energies are the energy of three independent oscillators. So this is and we also need to remind ourselves about the energy levels of one of these oscillators. So this is one quantum oscillator. And remember that that if we call the energy of the ground state E0, then this energy would be E0 plus h bar, what we've called omega 0, and this would be E0 plus h bar times, I'll write it 2 h bar omega 0, and that's etc., where this frequency omega 0 was the square root of k sub s over m, except these are atomic level quantities. So this is the interatomic bond stiffness. That's the mass of one atom. So it's the same relationship you got for a macroscopic mass and spring, but we're just talking about it on the microscopic level. Okay. So one atom, three independent oscillators, and each of these oscillators has this energy level structure that we are familiar with. And so we're down at the microscopic level, and it's important to remember that. And so we're going to call, here's the important thing, we're going to call this quantity h bar omega 0, or h bar times the square root of the interatomic spring stiffness over the mass of an atom. We're going to call this one quantum of energy. And it's just some number of joules. It's just depends on the bond stiffness and the mass of the atom, but it's just some number of joules. And you've done calculations where you've calculated how many joules, or it's about, what does it come out to? It came out to about a hundredth of an electron volt or something like that. So, but when we talk about the number of quanta, we're talking about how many of little packets of energy of that size we've given to an oscillator. So here we've put in one quantum of energy to oscillations in the z direction and 1 quantum in the y direction and 1 quantum in the x direction. But we could actually instead put all 3 of those quanta. That's putting 3 quanta into oscillations in the x direction. Okay? So we're going to keep talking about 1 quantum, and that's what we're going to mean